Procedurally generated content is an important part of any game. It makes the game different and feel new every time the player plays it. It's all about creating a random experience, but controlling that randomness enough to make sure everything fits together correctly. For my project, I created a random level generator that creates maps of varying sizes with both inside and outside pieces. This project has been a challenging experience, but I finished with a project that I'll be able to use and expand upon in many future projects. For me, the easiest way to create a procedurally generated map is to create a variety of pieces and then randomly select and spawn them into the world. In the past, I had made a randomly generated maze. However, all of the pieces had entries on all four sides, so all I had to do was choose a piece and add it in. While I could get away with this in a maze, this couldn't really be done with empty rooms, and I wanted to challenge myself as well. I wanted to expand on this idea by having more pieces with varying entries and have pieces spawned based on the pieces around them to ensure all rooms were cohesive. In the previous assignment, I created AI functionality that allowed enemies to interact with one another. I also added a new state, Investigate, where an enemy will actively seek out the player. My partner created a system that introduced varying types of nodes to simulate different types of terrain, such as fast nodes for something like icy floor, and a slow node for something like sand. Enemies still prioritize the fastest path, but the calculations are now affected by these new nodes. For this assignment, my partner is building off the AI from my previous assignment by adding in varying types of enemies with different stats. The number and types of enemies spawned in a level is determined by a specified difficulty rating. My project integrates with my partner's assignment by affecting the difficulty rating of the level based on the size of the map. For example, a small map will have fewer enemies, whereas a larger map will have larger quantities or more difficult enemies. It also integrates with my previous assignment by creating more advanced rooms and routes that the enemy must check. My project integrates with my partner's first assignment by creating rooms with their random nodes to create diverse and interesting paths for the enemies. One of the most difficult parts of this assignment was getting the various rooms to spawn in correctly. I had a lot of trouble getting rooms to spawn in that also had the correct collisions. I eventually found a tutorial, which can be watched at this link, which formed the base of my project. I used a modified version of his system that uses a persistent level and various non-persistent levels. The persistent level contains the constant features such as lighting and the sky sphere, and all of the non-persistent levels were a different type of piece that could be spawned in the map. These non-persistent levels could be duplicated and moved, which is how the various pieces are added into the map. For this all to work, I needed an actor class that would hold all of the information at a specific point in the map. Hence, MapChunk and its blueprint, MapChunk blueprint, were created. MapChunk has a few key variables. It has a string for the name of the piece on it, an array of map chunks that hold a reference to its adjacent map chunks, and a navigation node which allows enemies to move around the map. The most important part of this assignment is the naming order of the rooms. They use the following 4-letter code to determine what doors and walls are on each side of the room. The first index of the string always represents the upward facing direction. Second is right, third is down, and fourth is left. If it has its corresponding letter, for example U, then there is a doorway in the up direction. If there is a letter N, then there is a wall. So for example, the room UNNL has doors on the up and left facing sides and walls on the right and down facing sides. It's important to note that pieces aren't rotated when they are spawned, so maintaining this up, right, down, left order is crucial. In the level blueprint for each map chunk, it retrieves the room name that it has been assigned, finds the corresponding level with the same name, and then spawns it into the map. The initialize function then sets the spawned piece to its correct location and makes it visible. I now had pieces spawning in the map correctly. However, I was still specifying the piece that had to be spawned. I needed a way to create a grid of map chunks and create all of the rules that the pieces had to abide by. I created a new actor called Map Generator and also made a blueprint of this class. Map Generator has a blueprint callable function called createMap, which returns an array of map chunks. This function is called on the level blueprint, and the returned array is used to learn what room each chunk has. Map Generator has a variable called MapLength, which determines how large the square grid is going to be. When createMap is called, it adds 2 to this number. The reason this happened is because I wanted a ring of flat ground to surround the original map. I wanted this because if a map randomly fills in the grid perfectly, there would still be an outside ring which would allow for flanking by the players. After this, it then calls GenerateMap, which starts the creation process. First thing is to create the empty grid of map chunks via the function createMapSkeleton. It creates all of the empty map chunks, sets their position to be in the correct spot in the level, then creates a node at its position, and then adds the chunk to an array that holds all chunks. The next thing it does is sets up the adjacent chunks of the chunks. However, when this is calculated, it only determines the neighbors of the inner chunks. It basically pretends that the outer ring does not exist. This is because I wanted to determine what positions the player could enter/exit the building. So it creates an enclosed building by treating the outer ring as a wall. Setting up the adjacent neighbors is pretty straightforward. It just checks for normal edge cases, however it just checks an extra row in. The next thing it does is that it determines a random start point for the map. It ensures that the random chunk is not part of the outer ring, and then it adds that to a list of chunks that need to be checked. Then it starts iterating over all of the chunks in that new array. It then gets the first map chunk of the array and adds a room to it. For a given chunk and an array of room names, it randomly selects one and assigns it to the room string variable. To determine which rooms could fit in the selected chunk, the determine valid rooms for chunk method is called. It takes a map chunk and returns an array of strings. The first step is to create a list of conditions that the new room must meet. Room conditions are an array of strings that each contain a single letter. These conditions are used later. For the given chunk, it checks all of the adjacent chunks starting from the top. If the chunk is a null pointer, then the chunk is on the edge and it will treat it as a wall. The letter n is added to the conditions. If it isn't a null pointer, but the chunk does not have a string, then the letter a is added, because a room with any letter can go there. A simply indicates that the wall does not require a door, but it can have one. If the room is not a null pointer and it has a room assigned, then we need to check for the connection. To check the connection, I needed to get a substring for the corresponding letter. Unfortunately, Unreal doesn't have a built-in substring function, or I just missed it. To get around it, I created a function in the map generator blueprint called createSubstring. I can't return a variable from the blueprint, so I created a string and set the result of the substring to the new string. Then I can access that string in the C++ file. So wherever you see new substring, it is just the most recent result of that function. To call the function, I use the function call function by name with arguments, then have a string with the name of the function and all arguments separated by a space. When checking neighbors, we need to get the opposite direction of the direction we are currently checking. For example, if we are checking up, index 0, we want to check down, index 2, on the neighbor above us. We then get the corresponding letter and check its value. If it's n, then n is added to the conditions, because a wall must be on that side. Otherwise, it is either U, R, D, or L, which indicates a door. So we want to add the opposite of the letter we just got, which is the direction we were originally checking. So if our neighbor has door R, then we need condition L. Once we have all of our conditions, we compare every room against those conditions. It first assumes that the room is valid and tries to disprove this by finding a breach in the conditions. It checks every direction of the room, and if it doesn't violate any of the conditions, then it is added to the list of possible rooms. So as long as the condition is an A, all directions must meet the specified condition. Then, as mentioned earlier, this list is passed on to the addRoom method, where one of these rooms is randomly assigned. Back in the while loop where rooms are added, we then check the adjacent rooms of the current chunk. If the room we just added has a doorway to another empty map chunk, then that chunk is added to the list of chunks to be checked. Finally, the first chunk of the array is removed, and this process is repeated until the map is finished. The next step is to set up the adjacent chunks of all neighbors, including the outside ring. It iterates over every node, clears their list of neighbors, and then recalculates them. This is done like before, except for the entire grid. Now that all neighbors are correctly calculated, we fill all empty chunks with a generic flat tile. The outer ring will always be filled, plus whatever other chunks didn't have a room assigned to them. The next thing is that we need to determine which chunks make up the perimeter or border of the building so doors can be placed. It iterates over every map chunk, and if one of its adjacent tiles is the filler piece, and it is a room, not another filler, then it is added to two lists. The first list is called All Border Rooms, and this contains multiple instances of each room. So if a room bordered 3 filler pieces, then it would be added to the array 3 times. Then it is added to another array, which tracks the number of distinct border rooms. Only one instance of each chunk can exist in this one, however. From here we select a random number of doors to create based on the number of distinct border rooms and the number of rooms created. The minimum value is 2 because there will always be at least 2 rooms in the map. Then it selects a room from the array of chunks with multiple instances. The reason I created this array is because it skews the probability of rooms that will have doors added to it. For example, a room bordering 2 filler pieces is more likely to be picked than one that only borders 1 filler piece. It then checks if the piece already has a door added to it. If not, then it selects a room with a door to the outside and then removes it from the list of distinct border rooms. This is repeated until all doors have been added in. Adding a door to a room works in the same way as adding any other room, except the possible rooms are slightly changed. The function determine valid door rooms per chunk is used. It works very similarly to determine valid rooms per chunk, except the conditions are calculated differently. It checks all 4 directions, and if it borders a filler piece, then it adds an A for its condition. Otherwise, if its neighbor is a room, it copies its current value for that direction to maintain consistency. Then it determines all possible rooms that meet the conditions as before, but before it is returned, the room string of the chunk is removed from the list. This is to ensure that it creates a room with at least one door facing outside, and the same piece can't be repeated. Once all doors are in place, it sets up all of the node connections. Nodes simply set up connections based on the neighbors of their chunk. For each chunk, it checks all of its neighbors to see if they are a null pointer. If not, it checks all directions of the current room. If the direction is a door, not n, then it checks if the neighbor has a matching door. This has to be done because the filler piece is called URDL, so it could neighbor a wall, which means we don't want a connection to be set up. If there is a connection, then the node of the neighbor is added to the connected nodes of the current chunk. Finally, the outer walls are scaled and moved to encompass the entire map to ensure no one can fall out. When the game is played, the player is spawned inside a black box outside of the map. This is done because it can take a moment for all of the rooms to spawn, and I don't want the player to fall through the map. And if you spawn it after the map has been done, you leave behind a default pawn which I didn't want in the scene. If I had more time, I would have gone with the second method and just removed the pawn from the level after the player had been spawned. Alas, players are spawned in the box, and after a set delay, they are moved to the bottom left corner of the map. There are a few other methods that are called after this, but these set up the AI of the map, which my partner will cover. But in short, all nodes are added to the AI manager, like in previous labs, and then it sets the difficulty based on the number of rooms, not chunks, in the map. Finally, it spawns all of the enemies based on that difficulty, and that sums up how I created my procedurally generated map in Unreal. There are a lot of moving parts, but they all fit together perfectly to create a great end result. For assignment 4, it should be very simple to convert to online multiplayer. The map will be generated in the same way on the server and then replicated to all of the clients. Each room would have their own spawn point, much like nodes, and a player will be able to spawn all over the map. For the next assignment, I will be sure to fix spawning to make sure that players start as a default pawn, and then that pawn is removed when their player is spawned in. Besides these 2 things, conversion to multiplayer should be straightforward. And that is my project. It was a lot of work, but I'm very happy with what I was able to accomplish. There's a lot I still wanted to do, and I would have loved to make it more efficient, because it currently does a lot of looping. There's also a bit of duplicated code that I would like to put into separate functions, such as comparing all rooms to a list of conditions, or setting up the adjacent chunks. There is a lot of potential with this project to expand upon it to give it more variety. One key feature would be to have multiple filler pieces to give the outside more variety instead of flat grass. Instead of having a set piece, I could use an array and randomly select a piece. I could also give these pieces random rotations because they all follow the same up, right, down, left rule. Similarly, there is a lot of room to expand simply by adding in more rooms. Adding rooms with corridors, smaller paths, and hiding places would be easy to create and would make each level feel even more unique. I definitely plan on using this map generator in future projects. After I've tidied it up, of course. Anyway, that wraps up my entire project. I hope you enjoyed watching and found this video interesting. I also hope it gave you some ideas for what you can add to your own projects in the future. Thanks for watching.